This is the Servotube STA1104. This is the coil for this little linear motor, and this is the magnet. It's actually a tube with magnets in it. It's pairs of north and south pole magnets, just like a linear motor. And inside here, there's a bearing at each end. So the aluminum slides across the plastic material bearing. I don't think there's a lot of side loading on it, but it allows it to move freely. It's a very clever device here. It reads the magnets for sine and cosine, and so the circuit in here, which we had helped develop at one time, but we've now sold this off to Dunkermotren. Anyway, so the sine, cosine, and feedback goes back to a drive. This is the Copley ACJ-S. This is an older, small, low-cost, can-open RS-232 drive for position control. And it works really good with this linear motor here. So we'll take a look at this motor and these drives. So I found this data sheet for the STA1104 on the Dunkermotren webpage. And it's got some healthy, continuous, and a lot of peak torque, short periods of time, 1 volt peak to peak sine cosine, 6 microns of repeatability. That's not accuracy. Accuracy is based on the pairs of magnets. We've got good data here for the currents and the electromechanical time constants. Good dimensional data, rod lengths. Good information about the feedback connections on this D-sub connector. I'm using their cable assembly here. That seems to work just fine. Motor color wires and ordering guide. So that's pretty good. I'm using an ACJ-S option for sine cosine, and I'm using an 090-03. You know, this is a 75 volt motor at the most. I'm running on 26 volts, so do not exceed 75 volts. There's another range of drives. These are the Copley EtherCAT and CAN-open. These are the plus drives. They also come with sine cosine. So there's packages like a module for integrating into a system, a 2-axis module for 2 axes of control. And I'm actually working with an EtherCAT application to drive 2 of these motors in a synchronous manner, kind of like a gantry with cross coupling. So this is a cool drive. I don't think we've implemented any position correction tables in the drive yet, but you know, that may be a possibility. You never know. We'll see what happens. So to get started, I used CME2 version 7.0. I'm going to call this the retro CME2. The cool thing about it is there's a Servotube button. So I just push the Servotube button, pick my motor, warning about 75 volts again. Position, velocity, current, CAN, whatever mode of operation your control architecture needs. Emulated output. I think we even did an ACJ once that did emulated Hall output. So, you know, there's many possibilities with this thing. And clear faults. So I'm connecting to the drive for the first time. There's the default interpolation rate. You know, maybe there could be more interpolation, but hey, you know, why have more resolution for repeatability than is possible, or accuracy than is possible? Anyways, the data comes in already. I didn't have to enter this. It's all part of the old 7.0. We can calculate the initial tuning parameters, and we can take a look at, you know, can we enable this thing and jog it? So I haven't done anything. I haven't done any tuning, and I get a kind of not very stiff, a little bit spongy loop here. But we're going to hook up CME2 version 7.1 to see how to configure this thing. You know, after we load up the data and save to flash. then let's see how it's really configured in the new CME2 version 7.1 that does not have the Servotube button. So change settings. This is a brushless linear motor. It has a low frequency analog feedback, and it has Hall type analog. So this is real important for configuring the commutation and the interpolation on the sine cosine. So that's a critical factor setting in 7.1 if you're using the new software that does not have the Servotube button. Everything else pretty much looks the same here. That's good. We can see our motor data. That's the same. We can see the interpolation rate. I'm just going to go down the list here, look at the current loop bandwidth. It's a linear motor. How much current loop bandwidth do you need? You're only going through so many electrical cycles per second. 400 hertz is fine. We don't want to overdo it. There's probably a 350 hertz limit anyways for the velocity loop based on the sine cosine filters. So we have to watch that. There's speed limit, some gain parameters, position loop, default parameters, that's all nice. Some trajectory limits, crazy acceleration, some pretty high speeds. We can crank that up if we want. So just going through the tuning practice here with a Servotube. With a small signal, we can see the gains of the current loop. If the integral is too high, then we get a little integral wind up. We want to back that down a little bit. So I can get a little bit more current loop bandwidth out of it. You know, there's some inductance here, and it's not a big power supply, so maybe I got a little slew rate limit here. So I could probably get a kilohertz current loop bandwidth out of this if I want, which is nice if I'm pushing the velocity loop real hard. So yeah, there is a pole output filter at 200 hertz, low pass Butterworth. I'm going to do a single pole. This is older drive configuration. The Plus drive has fancy filters and more configuration, so I'm just limited by the old ACJ here, which is fine. We're able to do really good control with that. So off to the velocity, auto setup checkbox, apply to velocity, velocity limit. Let's just knock this down to some earthly reasonable value here. I mean, it could do it, but that's a lot of acceleration. These are the default gains, velocity parameters, and I like to look at channel 3 current actual, and we'll take a look at this, see what happens. So yeah, maybe we should move it to the center. Let's accelerate a little bit more. So we'll do 10,000 for XL and decel. When the drive is disabled, we can move the rod to the center. All right, there's a normal profile. So let's check out the gain limit. Double it till it oscillates, then cut it in half. I hear the oscillations. I see it. 600. So this should back it down out of the oscillations. Yeah, I don't see much oscillation in the current loop. Pretty good steady state error. Pretty good getting to speed. So let's try. See if we can over integrate a little bit. And there's a little bit of integral wind up there. I'm just going to cut it in half and say that's pretty good for now. And let's stop that. We'll go to a profile tab, auto set checkbox, channel 3, current actual, and 4096. 4096. That's the interpolation off of a magnetic pair length, 25.6. So I guess it goes 25.6 millimeters for 6.25 micron repeatability. So just checking out how far we plan to see this thing move. We moved an inch in the forward direction, or 25.4. I could use a little bit more integral here. So let's go back in the negative direction. Let's give it a little bit more integral there. So, yeah, I'm not over integrating here, so I think this is good. Let's do that again. 40, 81, 92. So let's make a fast move in this direction. We're almost getting to our profile limit. Let's just set this to 1 meter a second. Go back out. There we go. So we're hitting the speed there. So just be careful here. There's no physical limits attached to this thing. That'll launch like a rocket or a bullet. I'm going to make a 4-inch move here, and let's see if this occurs. That's not too fast. Let's see what this puppy can do. Yeah, the tuning looks pretty good. A little over integral there. I might take that integral gain back down to where I had it. The system moves a little bit because I don't have it bolted down. Let's go in the negative direction. And let's make a really fast move. Let's see if I can do 2,000 in the positive direction. Yeah, that did it. Yeah, that's pretty good. I need to increase my accel and decel. No load here, so that should be able to do it. And let's put a limit here so I don't exceed that limit. So faster accel, faster decel. I'm going to have to go a further distance to actually get to this speed. So yeah, I'm hitting 2,000. Let's do 2,500. Well, I can do that still. And my currents are hitting 6 amps. So see if I can get up to 9 amps with this sucker. So I want to go in positive direction. Fingers crossed. Hope that's the right way. Whoa! Launched it. Yeah, that's too fast. Following error. I was hitting a limit. Following error built up. Probably clipping the peak current limit there. Oh, I got 12 amps. Let's bring that accel back down here. A little bit more reasonable. Disable, clear faults. No, there's no magnet in there to do control with. Clear faults. All right, we got the feedback cooking now. There's that move. Oh yeah, little building following error, not quite hitting the speed, but almost. We'll take a look at the velocity limit based on the voltage. Voltage terminal servo. And event warning, voltage limited. We could move in the positive direction. Oh, almost launched it that time. Yeah, so that speed's a little too high. We're starting to hit the power supply limit there. So we'll bring it back down to something else. Alright, let's see if we can do. Still hitting a little limit. So the back EMF on this motor is 4 volts per meter per second, plus some IR drop. So yeah, geez, if I had 10 amps and 4.9 ohms, that's like 50 volts. So if I had a 75 volt supply, I could go wicked fast. I got some IR drop and some voltage limit warning here. So these speeds are a little excessive for a 24 volt supply. But like I said, we can do 75 volts with this motor, so no reason to have a voltage limit. So here's a well-behaved move with no limit. The following error comes down, plus or minus a count or two, and then some error while we're accel and decel gets to stay.